Hi, good morning, class. I wanted to take a few minutes to give you some more information about the Earth's atmosphere. We left off the other day talking about one of the main differences between the layers in the atmosphere, and that was temperature. Temperature changes are not consistent throughout the atmosphere. And as we discussed in the troposphere, the temperature actually decreases as you get higher, but then something happens in the stratosphere and the temperature increases. Then once you get into the mesosphere, it decreases again, and in the thermosphere, the particle temperatures get hotter and hotter as you get higher, closer to space, but the actual area between the particles gets it gets colder. So I just wanted to review this before we started into another difference in the 4 layers. That difference is air pressure. Before we start talking specifically about air pressure, let's just talk about what pressure is in general. When something is creating pressure on another object, it is exerting a continuous force on that object that it's in contact with. So when we talk about air pressure, air molecules are creating a pretty consistent force on whatever it's in contact with. So you might be wondering, and I think some of you have asked in class, well, how much is the atmosphere pressing down on us? And if you take your fingertip is about 1 square centimeter. And if you can imagine holding about a 2-pound weight, that's how much pressure the atmosphere is pressing down on us. If you aren't sure what a 2-pound weight would feel like, picture a really big can of baked beans. That's about 2 pounds. So just holding that up with 1 fingertip. Why don't we feel the air pushing down on us? It doesn't feel like I'm holding tons of weight on my body. Well, that's because air not only pushes down on us, but because it's all around us, it's pushing in on us and up on us as well. I'm going to do a demonstration about air pressure and how it pushes in all directions and what its effects can be on an object that it comes in contact with. Alright guys, so I have a glass jar here, and I'm simply going to, it has water in it, there's no lid on top. I'm simply going to just place the index card over it. So for describing the experimental setup, this is what you're describing. Now, kind of think in your head, what's going to happen when I take this jar and I flip it over? Alright, well let's see what does happen. How many of you thought that that would happen? Let's talk about why it happens. When I flip it over, the water is being pulled down to Earth's surface. But air pressure is also pushing up on it and on the card. So the air's pressure forcing up is equal to Earth's gravity pulling down. And that's why the water doesn't come out. Now, let's try something. Alright, so we're going to try something else. Now, I have got an index card with a hole in it. Alright, so I have this index card with the hole in it. And we're going to flip over this now. What do you think is going to happen? Well, let's find out. Now we're going to try something different. I have water in my jar again, but this time I have an index card that has a hole in it. I did make it a little wider just so that the edges came way past the glass. But I have this over it. What do you think is going to happen now that I have a hole in my index card? Is the water going to come out, or is it not going to come out? Let's test it. Flip and hold. It worked for a second. You could probably see it that there was some time. There were some gaps around the edge that allowed the water to come out, but when I had that flat surface on, it didn't come through the center hole that was in the index card. Why is that? Because gravity pulling down on the water was pulling down just as much as air pressure was pushing up, not only on the surface, but also through this hole. It was pushing up on the surface of that water. We're going to do this one last time. This time, I'm going to put wire, and there are holes. I don't know if you can see clearly, but there are holes in my lid. So instead of just having one hole now, we have several holes. And I'm going to tip this jar over. What's going to happen? You can see that some of it came out, but you can also see that there's still water in my jar. And it is because, again, the force of gravity pulling down is equal to the force of air pushing up. So air is not only being pulled down towards the ground due to gravity, but it's also pushing up, and it's going to be pushing in on this jar. We're going to do several labs this week that go over the fact that air pushes in all directions. It's not only pulled down by Earth's surface to push down on our shoulders, but also in all directions on all parts of our body. Alright, so moving on. We're going to talk now about the three factors that affect how much air pressure the atmosphere has in it at any given time. Because air pressure does change. So what makes it change? What makes it increase or decrease? There are three factors: water vapor, elevation, and temperature. If you see, the acronym that we might be able to remember is WET. W for water vapor, E for elevation, and T for temperature. Those are the three factors that affect the amount of air pressure in the atmosphere around us at any given time. Let's talk more specifically about these three. Water vapor. Water vapor, when there's more of it in the air pressure decreases. And that's called a negative correlation. More water vapor, less air pressure. The reason for this is water vapor molecules are less dense than most other gas molecules in the air. They're about the same size as other molecules, but they don't have as much mass. And because of that, they have less density, and it makes the air less dense. When something's less dense, it can't put as much force on other objects. Kind of think about it as water molecules being a beach ball and regular molecules being a bowling ball. Which one would be able to apply more force on something else? Now let's talk about elevation as a factor that affects air pressure. As elevation or altitude increases, air pressure decreases. So again, this is a negative correlation. As one does one thing, the other factor decreases. So why is this? Well, there's a few reasons. You have learned that as you go higher up in the atmosphere, there are fewer and fewer gas, liquid, and solid molecules. So therefore, there are less air molecules to actually push on different things. Also, the farther you go up in the atmosphere, there's less atmosphere above you. So gravity pulling down, there's not as much above you to be pulling down on top of you. So that's why the further you go away from our surface towards space, the air pressure decreases. Here's a diagram that kind of shows you a little bit about what we're talking about. We have this Eskimo guy who's at the base of a mountain and on top of a mountain. Check out the blue particles. It shows you kind of a correlation between how many are there in the atmosphere at different levels and what the pressure would be. Last factor is temperature. Temperature, as it increases, air pressure decreases. Are you noticing something? This is also a negative correlation. So as temperature goes up, air pressure goes down. This is because when there is a higher temperature, particles are moving faster. So the air particles are moving faster and they're also spreading out. So the density of the air in general is decreasing because it's taking up more space, but it has the same amount of mass. And therefore, with less particles in that area to press on things, the air pressure would be less. Now, you might be wondering, is there anywhere on Earth that doesn't have air pressure? And the answer is no. Everywhere on Earth and in Earth's atmosphere has at least a little air pressure. And that air pressure can change depending on those three factors: water vapor, elevation, and temperature. The labs we're doing over the next couple of days will help you understand how these factors affect air pressure. The only area in the universe that wouldn't have air pressure is a place where there is no air, a space void of all matter, and that is a vacuum.